Hello, you're welcome. All right, now the topic we are gonna be looking at in this tutorial is vectors. Okay, now vectors actually goes with scalars. All right, scalar quantity. So in physics, it's either we classify a quantity as vector or a vector quantity or it's a scalar quantity, right? So now the question is, what is a vector quantity? Okay, now a vector quantity in physics, okay, any vector quantity has two things, okay, in common, in that they can be expressed in direction, okay, as well as magnitude. So they are the quantity that can be expressed in direction and magnitude. All right, so you don't just use the size of the vector to represent the vector. You also need to express the direction at which that vector is acting. All right, now for example of vector quantities have force. Okay, now if I describe a force to be a force of 20 newton, all right, 20 newton is the size of the force or the magnitude of the force, but then the 20 newton is not um, a complete information. Okay, I need to actually express the direction this 20 newton is actually acting. Okay, is it acting at an angle 30 degrees, all right, to the horizontal, right? Because the direction at which this particular force is actually acting, okay, will definitely affect its resultant magnitude, right, in a particular direction. So please take note. So example of vector for quantities are force. All right, I'm giving you one example, and of course others. We have velocity. Velocity is also a vector quantity. We express it in direction and a magnitude. We have acceleration. A vector quantity also. We have momentum. Then etc. All these are vector quantities, right? So please take note of them. But in the case of a scalar quantity, right? Now, what makes scalar quantity to be different from vector quantity is that they can only be expressed in their magnitude, their size. All right, so, and of course, example is time. Okay, time only has magnitude, right? Length also has magnitude. The length is just a distance, the distance between 2 points. Okay, just a magnitude. Even temperature has magnitude. Work, right? Work can only be expressed in magnitude, right? And of course etc. So these are scalar quantity. Now in this tutorial we are going to focus our attention in vector quantity, right? So now we are going to look at how we represent vectors, right? Representation of vectors. All right, now if I need to represent a vector, okay, always take note that I'm representing two things. First, the magnitude of the vector, and of course I'll still need to represent the direction of the vector in the space. All right, so there are two ways to actually represent that. We have two dimension. Okay, two-dimensional representation of vectors. Now if I'm representing a vector in two dimension, okay, I'm considering the fact that that vector is actually located in a plane. A plane is actually, okay, a surface that I can represent using two axes. One is vertical, the other is horizontal. Okay, a plane has these two reference axes, vertical or horizontal. Then it can be in between, but this is, it must, okay, is basically can be represented, okay, with two axes. That means if that particular force is acting vertically, all right, or if that vector is acting vertically, I can use this to represent its vertical dimension. If it is acting horizontally, I use this to represent f of x, to represent its horizontal dimension. But if it happens to be acting, okay, at an angle, neither vertical nor horizontal, okay, then definitely it has two components. All right, one component is a component in the horizontal reference in the horizontal dimension, and that component is a component reference in the vertical dimension. Okay, so that means if the force is F, then for me to represent this, all right, of course if you want to represent a vector, use bar. Okay, they write the symbol of the vector then with bar on top of it. So this vector F, which of course is neither horizontal nor vertical, is going to be represented with, okay, the combination of its vertical component, or let me start with the horizontal component plus its vertical component. All right, so both the vertical component and the horizontal component is what represents this particular vector. Now in some cases, okay, we actually attribute a unit vector in the vertical direction, that is f of y, to be j, and one in the horizontal direction to be I. Okay, so I have coordinate I and j. So if a vector is actually found itself, all right, neither vertical nor horizontal, I'll use this coordinate to represent it. All right, for example, if I have vector A, okay, having a coordinate of 2, 3, okay, is something as actually expressing A to be equal to 2i. That is the vertical component of A, right? Then plus 3j, which is the horizontal component of A. So please take note of that. So that is representation of vectors in two dimensions. Now what you're going to be doing here in this tutorial is to find, okay, we're going to be looking at how to evaluate the resultant. Excuse me, we're going to look at how to evaluate the resultant of just two vectors. Okay, resultant of two vectors in a plane, right? In a plane dimension, okay, in two dimension, right? In two dimension. Now we're going to look at some cases. We're going to look at some cases of resultant. So we look at the very first case, case 1. And before the, okay, let's define the term resultant. All right, resultant of two vectors is actually the result of adding those two vectors together. Okay, for example, if you have two forces, okay, two forces, let me use the very first case, excuse me. If I have a weight, a beam, all right, and I have two forces pulling on this beam, in the same direction, and I call the first force F1, then the second force I call it F2. All right, so if I need to get this resultant of these two forces, all right, since two of them are acting in the same direction, and that is the horizontal, right, f of x direction, okay, and of course if I should, two of them are having they are in the same horizontal direction, that of course their component is going to be I. F1 is I, F2 is I. Okay, so if I need to get the resultant is the actually the resulting, okay, vector when I actually add up this. So this is gonna be, the resultant is gonna be this F1 plus F2. Right, they are acting in the same direction, right? So I have to add it up. That's going to be the result, and that the sum of adding these two vectors together, right, gives me, that's what I have here as R. Okay, so I can have this. All right, so please take note of that. Now let's look at case 2. Now in case 2, you have these two vectors acting in opposite direction. So that is, one is positive I, the other one is negative I. All right, one is positive, so let me call this F1. Then the other one here acting in opposite direction, I call it F2. So the resultant of these two vectors is gonna be equal to, this is F2 is acting in the negative direction, F1 is acting in the positive direction. Okay, so if you need to sum it, that's going to be F1, which is positive, then minus F2, which is negative. All right, so invariably now, if this is 20 Newton and this is 10 Newton, so the resultant is simply the same as, okay, that's going to be 20I, right, minus 10I, because I will use I to represent vector, okay, in the horizontal dimension, right, a unit vector in the horizontal dimension. So that's going to give me 10I Newton, right? So please take note of that. I'm using force as my illustration. Okay, so now I proceed. I'm going to look at different scenarios, right? The next scenario I'm going to be looking at is a scenario where those two vectors are inclined at an angle to each other. at an angle. Alright, so now let's see, you have I will draw my coordinate system. I'll draw my reference axis, vertical and horizontal, right? Then I have the two vectors. Okay, let me call the one F1. Then I call another one, okay, F2. So, and the angle between them, let me call it theta. Alright, so now if you're being asked to evaluate, okay, of course you know that this vertical is this f of y, f of x. So if you're being asked to evaluate the resultant of these two vectors, f1 and f2, incline at an angle to each other, okay, now we're going to apply what is a law known as parallelogram law of vectors. Parallelogram law of vectors. How does that work? Now, according to the parallelogram law of vectors, okay, if I have two vectors incline at an angle to each other, okay, of course, I've already given them f1 and f2, right? f1, let me use this as f2, okay. For which actually find this the resultant of these two vectors, I can represent these two adjacent vectors, they're adjacent to each other, right, because they're inclined at an angle, by the two sides of a parallelogram. So that means this, I want to draw two sides of a parallelogram, one parallel to each other, okay. So this now is parallel to f2, then of course I join it to this is, this side is parallel to f1. So I use this adjacent side of a parallelogram to represent these two vectors, okay. So now according to the law, if I can use the adjacent side of a parallelogram to represent two vectors inclined at an angle to each other, right, then the resultant of these two vectors is going to be gotten by the diagonal that join the two vectors. But every parallelogram has a diagonal, right? So, and that diagonal, call it R. So which simply means that the diagonal R, okay, becomes the sum of the two vectors, okay. That is going to be f1 bar plus f2 bar. Of course, we use bar to represent. Now this is how I will actually express the resultant of these two vectors in form of diagonal, all right, in form of their unit vectors, right. Now remember, both f1 and f2 vectors, as you can see from this diagram, all right, none of them is neither is horizontal nor vertical, they are inclined at an angle. That means both f1 and f2 have the two components. f2 has the two components of vectors, both vertical and horizontal. I told you that anytime a vector is inclined at an angle, all right, it's neither horizontal nor vertical, it will have these two components of vectors I and j. f1 will also have the two components of the vector, which of course is also I and j, right. So now, if that being the case, let's say let me give let's say vector f2 has a coordinate of s2 comma y2, right, and vector f1 has a coordinate of x1, okay, from the origin, all from the origin, okay, and of course y1, right? So what simply means that if I should represent f2 in its unit vector, of course you know that that's going to be x2i plus y2j, right? X is for I, Y is for J, alright? Then of course, if I should represent F1 in its unit vector, that's going to be x1I plus y1j. Okay, combining these two now in this formula, so I can simply say the resultant of these two vectors is going to be equal to the combination of this, okay, the component of this, right? x1I, right, plus y1j. The same thing happen here. Have x2i plus y2j. Okay, so of course you know what happens. Collecting light terms, si and s2, they are light terms, right? So that's gonna be s1 and s2 because they have their light term. Why? Because they have I, right, as their unit vector, right? So I can actually bring them together, then factorize. That's gonna be I into x1 plus s2. Alright, then the same thing happen with y. So j becomes y1 plus y2. So I hope excuse me, that is well understood. Okay, now let me give you a typical example. Okay, so the question is, what is the resultant? What's the resultant between? What's the resultant of A equal to 2I minus 3j, then comma B equal to 5I plus 6j. Okay, then you are being asked to express it in magnitude. So you have to express your answer in magnitude and direction. Okay, so now solution. So if I'm to solve this, right, these two vectors, right, are being expressed in terms of now these two vectors are being expressed in terms of their unit vector. Then I have to find the resultant. Applying the parallelogram law of vectors, right? You know how we'll do that. I have to add them up. That's going to be 2r minus 3j plus 5i plus 6j. Of course, collecting like terms together, that's going to be 2i plus 5i gives me 7i, right? Then minus 3j plus 6j gives me plus 3j. So this is the resultant in terms of its component, alright? Now you can express a vector in terms of its component. This is for horizontal component of the vector, and this is the vertical component of the vector. But now, since we are being asked to express this vector in magnitude, alright? The magnitude, remember, is a scalar value. The one single value that represents the vector r. This is just a component of the vector r, right? How do you express the magnitude? If you are being asked to express the magnitude of a vector, right? Let's say any vector. Let's say vector A that has a component axi, right? Plus ayj, horizontal and vertical, right? So the magnitude of this vector, we use modulus A to represent that, and of course it's given us the square root of, okay, ax, the horizontal component squared, then plus ay, right? The vertical component square. So please, this is how to express the vector magnitude, right? Now if you want to get the direction of the vector, the direction is the angle theta between the resultant A and any of these vectors, alright? So to get the direction, theta, alright, is going to be equal to the tan inverse of the vertical force, which of course is ay, divided by the horizontal force, ax, okay? This is the direction. So now applying now to this question, right? My resultant, now the magnitude of my resultant r becomes the square root of course, 7 square plus 3 square, right? This is going to be 7 square plus 3 square. So which is going to give me, of course, this is 49, right? Then plus 3 square, 9. So invariably now having this going to be this square root of, what am I having? 58, right? Yes. The square root of 58. That is the magnitude. Then the direction theta, right, is gonna be tan inverse of the vertical component, okay, which is 7, divided by the horizontal component, which is 3. Alright, and just use calculator and evaluate that, and you're good to go. So I hope we are flowing. So resultant is simply adding those two vectors, okay? So, and as you're adding the vectors together, you consider the fact that a vector can have two components, has horizontal and vertical component, right? So you know exactly what you're doing. So with what we have so far, I think we can actually look at questions, a whole lot of examination questions, right? Okay, so that you will get to appreciate this topic better. All right, I will just see if I can look for questions. Okay, just give me some moments. Let me get some questions. Okay, so here we are. I wanna get question. Okay. Okay, so let's look at this system. Okay, we call this a system of coplanar forces. Okay, it's a vector. Okay, so the question is, what is the resultant forces, the resultant forces of the system shown above? Shown above. All right, so as you can see here, now this is a system of forces. If I should count it, it is 1 2 3 4 5. 1 2 3 4 5. Yeah, 5 forces. Now 2 of it is actually vertically represented, right, in the z direction. One upward, one downward. Then 2 of it is horizontally represented, right? The one is inclined triangle, and of course this one that is inclined triangle has both vertical and horizontal components. Now as you can see, I was only given the magnitude of the vector that is inclined triangle. I wasn't given the two components. Remember, if I want to add it, it will be easier for me to add it in terms of component, alright? So now I want to express this 3 Newton in terms of its component. Remember, in terms of its component, okay, it will have both vertical and horizontal component, alright? If I should draw a line, okay, analysis to meet the horizontal, you know that this is 90 degrees, right? So vertical component of this 3 Newton, if I should express it, that's gonna be, if you want to do the vertical component, that is, this is vertical component of the 3 Newton, f of y. Vertically, horizontally, you call it f of x, alright? The f of y of this, of 3 Newton, okay, is gonna be equal to 3 multiplied by sine of the angle, sine 30. Alright, y is horizontal, f of x. When you look at it horizontally, of course horizontally I have this is adjacent, right? Now someone will ask a question, how do I get this 3 sine 30 as the vertical component of 3 Newton? I think maybe probably I will teach you that before I now bring it. Let me just remove that. Let me show you how I got it. Alright, this is the 3 Newton in question. This line is for 3 Newton in question, right? This is the horizontal axis. So if I join this horizontal axis with this 3 Newton, you discover that what I have is gonna be a right angle triangle. Okay, so I'm looking for two components. So this is vertical, I'll call it Fy. This is horizontal, I'll call it Fx. And this is the angle theta. And of course, you know that Fy being on the side opposite to the angle theta, alright, becomes the vertical, alright, and this is the adjacent. So if I want to get the vertical component, Okay, vertical component. You know what I do, right? So hypotenuse, and of course the vertical is hypotenuse of this triangle, and of course the vector itself is, sorry, the vertical is the opposite of this triangle, and the vector itself is the hypotenuse. So of course you know the ratio that goes with that. The ratio that goes with that is sine theta, which of course is the vertical f of y, right, divided by the 3, the hypotenuse, right? So if I cross multiply, I now have that f of y is 3 sine theta. Alright, the same thing if I want to go for horizontal component. If I want to go for horizontal component, so what you would notice in this case is that the horizontal is the adjacent, okay, quite well. And of course the vector that I'm looking at is the hypotenuse. That cos theta goes here. So I have cos theta. Then cos theta becomes right adjacent f of x, then divided by the hypotenuse, which is 3. So if I should cross multiply, I have f of x to be equal to 3 cos theta. Alright, so vertical about sine theta, the vector multiplied by sine theta, horizontal, the vector multiplied by cos theta. Okay, so that is the proof to what I did there. Alright, so going back to what I have here, so I can simply say that this vector, okay, is a combination of both vertical and horizontal, right? So that means this vector here can be represented as 3, right, for horizontal cos theta. Remember, for horizontal, alright, component, the unit is I, alright, then plus 3 sin theta, and the unit is J. Alright, don't forget that this 5 here, the unit is I, 3 here, the unit is I, this is here, the unit is J vertically, the unit vector is J, right? So you know how we sum. So my result and the solution. Alright, solution. So my resultant is gonna be R. Vector R is my resultant, alright? The sum of all those vectors, okay? So let's sum it. Let me start with the one that's inclined, okay? So I have 3 cos theta I direction, okay, then plus 3 sin theta J direction. Alright, then plus, let's look at horizontally. Horizontally, I have this 5 Newton in the I direction, that is positive, positive 5 Newton. That is a couple 5 Newton, 5I, right? And this is negative, right? Negative S direction, negative 3I. Then plus positive 6J. Then negative 2I. Alright, you know how we do this. We have to collect like terms together, right? Collected like terms together. Okay, of course, this theta here is 30 degrees, right? So I'm gonna have 3 cos 30, alright? All the like terms plus 5, right? I, then minus 3. All these components are I component. If I factorize it, that's going to be I. Then plus my J component. What do we do? Okay, open bracket, starting with 3 sine theta. Okay, plus, right, 6j. Okay, I didn't add up the negative j, did I? Okay, I did. This negative j, right? Plus, okay, 6j minus 3j. Okay, just I'm factorizing now, so I just going to do 6 minus 3, then j. Okay, so with what I have, as you can see, okay, I can still break it down, right, into 3 cos theta, right? 5 minus 3 here is 2 plus 2. This for I. Then of course 3 sin theta, right? Then this is minus 3. This for j. Alright, so this is the resultant in terms of, okay, the two components I and j. Now remember, the resultant, we need to get it both in magnitude, right, and in direction. So to evaluate this resultant, right, in magnitude, of course, we express it as modulus. Alright, so that's going to be equal to, you know how we do this, right? 3 sine 3 cos theta, right? Three cos theta plus 2 all square. This is also plus, right? 6 minus 3 is plus. Then plus, open bracket, 3 sine theta plus 3 all squared. So it's just a very simple procedure. And of course, if you want to get the theta, the direction, okay, so that's going to be tan inverse of the vertical, right, and the horizontal. So that's just the tan inverse of f of y all over the f of x. Alright, so it's very simple way of evaluating the resultant of vectors. Right, so once you can express them in their horizontal and vertical component in terms of the unit vector, it is easy for you to add them up, subtract them, right, add or subtract. Then after doing that, you can always get the magnitude by applying this particular theorem. And of course, this theorem here is Pythagoras theorem. So now we're going to look at typical examination question. I think with what I'm doing so far, okay, no matter how complicated the question is going to be, I'm very sure that you will tackle it. All right, let's do that shortly in the next video. Thank you.